Welcome to Pump Design Lab. In this video, we look at one of the most practical topics in pump engineering, the free vortex and why swirling flow speeds up as it moves toward the center. We will then connect that behavior directly to what happens at a real pump intake and what engineers can do about it. Let's get started. Look at this pump intake. At first, the water around it may appear completely normal. But even a small amount of rotation in the approaching flow can become important as the liquid moves toward the intake. As the flow converges, that rotation can become stronger. And under the wrong conditions, what begins as a simple swirl can develop into a strong vortex near the pump intake. This can disturb the flow before the liquid even reaches the pump. So, the important question is, why does this swirling flow become faster as it moves toward the center? To understand that, we need to understand the free vortex. What is a free vortex? A free vortex is a rotating flow in which the liquid is not continuously forced to rotate like one solid body. The fluid already has some rotational motion. And as that rotating fluid moves inward, something very interesting happens. The swirl becomes faster. Fluid moves inward. Imagine following just one small particle of water. At first, it is rotating relatively far away from the center of the vortex. Now allow that particle to move inward. The distance between the particle and the vortex center becomes smaller. That distance is what we call the radius. Large radius. When the particle is far from the center, the radius is large. At this location, the tangential or swirling velocity is relatively lower. So we have a large radius and a comparatively slower swirl. Keep this condition in mind. Radius decreases. Now move that same particle closer to the vortex center. The radius becomes smaller. We haven't suddenly added another motor, and we haven't deliberately increased the rotational speed. But the particle is now moving closer to the center while still carrying angular momentum. Swirl speed increases. As the radius becomes smaller, the tangential velocity increases. In very simple words, move inward, spin faster. This is one of the most important characteristics of an ideal free vortex. The closer the rotating fluid moves toward the center, the stronger the swirl becomes. Simple relationship. We can represent this using one simple relationship. Radius multiplied by tangential velocity remains approximately constant in the ideal free vortex model. So if the radius decreases, the tangential velocity has to increase. You don't need a long mathematical derivation to understand the main idea. Just remember, radius down, swirl velocity up. This behavior comes from conservation of angular momentum. Forced vortex versus free vortex. This is very different from the forced vortex. In a forced vortex, the liquid behaves approximately like a rotating solid body. The farther we move away from the center, the higher the tangential velocity becomes. But in a free vortex, the trend is different. As the fluid moves inward and the radius becomes smaller, the tangential velocity becomes larger. So, remember the difference. Forced vortex. Outside moves faster. Free vortex. Inward means faster. Simple analogy. A simple way to visualize this is with a spinning skater. When the arms are extended, the rotation is relatively slow. When the arms move closer to the body, the rotation becomes faster. The water in a pump intake is obviously not a skater. But the same angular momentum idea helps us understand why rotating water can speed up as it moves toward the center. What happens to pressure? Now we need to look at another important part of the vortex. Pressure. The fluid is continuously traveling along a curved path. And to maintain that curved motion, pressure cannot be the same everywhere across the vortex. Pressure variation. Away from the vortex core, the pressure is relatively higher. As we move toward the center, the pressure becomes lower. So the vortex develops a low-pressure region around its core. This pressure variation is a very important part of the vortex behavior. Surface depression. At a free water surface, that lower pressure near the center can pull the surface downward. This creates the familiar depression that we associate with a visible vortex. As the vortex becomes stronger, the depression can become more noticeable. But remember, not every free vortex needs to form a dramatic air core. The visible shape depends on how strong the vortex becomes. Ideal trend. Now look at the ideal free vortex relationship again. If tangential velocity increases as the radius decreases, the mathematical trend rises sharply as we move toward the center. That creates an obvious question. Does the velocity become infinite at the exact center?
No.
A real fluid does not behave that way. Real vortex core. Very close to the vortex center, the simple ideal free vortex relationship is no longer sufficient. Viscosity becomes important, and a real vortex develops a finite core. At the exact center, the tangential velocity is approximately zero. Moving outward through the core, the tangential velocity increases. It reaches a maximum near the edge of the core. And farther outside, the behavior approaches the free vortex trend. So use the ideal equation to understand the overall behavior. But do not imagine infinite velocity inside a real vortex.
Back to the pump.
Now, let's connect all of this directly to pump engineering. A vortex is not important to us only because it is an interesting fluid mechanics phenomenon. The real concern is what happens when strong swirling flow approaches the pump intake. Good inlet flow. Under a good intake condition, the incoming liquid should approach the pump in a reasonably controlled way.
The flow should be steady.
It should be reasonably uniform, and it should contain as little unwanted swirl as practical. This gives the pump a much better inlet condition. Swirling inlet flow. Now compare that with a strong swirling approach flow. The liquid is still moving toward the pump intake, but it also contains a significant rotational component. As that rotating liquid converges toward the intake, the swirl can intensify. The pump is no longer receiving the clean inlet condition that the hydraulic design expects. Same pump, different inlet. Notice something important. The pump itself has not changed. The difference is the condition of the incoming flow. On one side, we have a relatively uniform approach. On the other side, we have strong swirl and a distorted inlet condition. Same pump, different inlet flow, and potentially very different behavior. Cause and effect. The useful way to understand this problem is as a chain. First, we may have a poor or non-uniform approach flow that creates or strengthens swirl. The swirl then produces a distorted inlet condition. And finally, the pump responds to that poor inlet flow. This is more accurate than simply saying that every vortex directly causes a pump failure. Possible consequences. If the vortex becomes severe enough, several operating problems may appear. Air can be drawn into the intake. The pump may experience vibration. The inlet flow may become unstable. And under some conditions, the poor inlet condition can contribute to cavitation-related problems. But the important phrase is, if the vortex becomes severe enough. A small visible swirl does not automatically create every one of these problems. Where does the swirl come from? So, where does the initial swirl come from? Often, the problem begins upstream of the pump. An upstream bend can create non-uniform approach flow. A nearby wall can make one side of the flow behave differently from the other. An obstruction can create a wake. And an asymmetric approach can introduce rotation before the liquid even reaches the pump. So the vortex we finally observe near the intake may actually begin much farther upstream. Design objective. The design objective is therefore simple. Give the pump a good inlet condition. The flow should be as uniform as practical, as steady as practical, and unwanted swirl should be minimized. Good pump performance begins before the liquid reaches the impeller. Check upstream first. So if strong swirl or a visible vortex appears in a real installation, don't immediately blame the impeller. First, inspect the intake system. Look at the approach flow. Check the available submergence. Look for nearby structures that may be disturbing the flow. And observe whether visible swirl is already developing upstream of the intake. The source of the problem may exist before the pump itself. Possible corrections. The correct solution depends on the actual installation. In some cases, improving submergence may help. In others, the approach flow geometry may need improvement, and some installations may require dedicated anti-vortex measures or flow guiding devices. There is no single universal correction for every pump intake. The solution must match the actual geometry and operating condition. Interview question. Now, imagine this appears in a technical interview. The interviewer asks, "What is the difference between a free vortex and a force vortex?" You do not need a long answer. Focus on the physical difference. Interview answer. In a forced vortex, an external influence maintains the rotation, and the liquid behaves approximately like a rotating solid body. The tangential velocity increases as we move outward. In an ideal free vortex, angular momentum is approximately conserved. So as the radius becomes smaller, the tangential velocity increases. Force vortex. Outside faster. Free vortex. Inward faster. That is the simple difference to remember. Takeaway 1. Let's summarize the lesson with 3 points. Number 1. A free vortex speeds up as the fluid moves inward. As radius decreases, tangential velocity increases. Takeaway 2. The vortex core is a relatively low-pressure region. That pressure behavior can create the characteristic depression at a free surface. Takeaway 3. Good pump performance starts upstream. Strong swirl at the intake can distort the flow reaching the pump. So controlling the inlet condition is an important part of good pump system design. The next question. Now we understand how a free vortex develops and why strong swirl at the pump intake can become a problem. But there is one more important question. What happens when that already rotating liquid actually reaches the impeller? Next video bridge. If the liquid has swirled before it enters the impeller, the incoming velocity seen by the blade changes. That can affect how the flow meets the blade leading edge. And ultimately, it can influence pump performance. So the next engineering question is, what does pre-swirl do to the impeller and the pump performance? That is where we go next. Thanks for watching. If this helped you understand the free vortex and pump intake behavior, subscribe for more pump engineering videos. The next one looks at what pre-swirl does to the impeller and to pump performance.